This is where we stop on the previous well test session called Well Test Theory and Practice. So we were dealing with a vertical well in a gas condensate reservoir in the North Sea, and we used the conventional derivative to drive the analysis. We match our model with an interpretation model using a vertical well in an homogeneous reservoir and with the presence of parallel faults. Okay, homogeneous, so that's a single layer with a uniform cage throughout, and parallel faults with a fault at 300 and 550 feet from the well. Small permeability, also you can see that here 2.5 millidarcy and a high skin, which might imply that we've got some limited perforation. You can see as well this large skin with this large hump here. We use the semi-log plot or superposition plot as a verification tool and also to help us to tweak the initial pressure. And we use the data plot as well as verification tool. We managed to match this PBU, the final PBU, quite well. But if we look at the previous PBU, the match doesn't look that great. So if we zoom in, like this, so now we can see that we overestimate the pressure for previous PBU. And looking towards the left, you can see that the discrepancy between our model and the actual data is getting worse and worse. Okay, the match kind of degrades. And if we look early on, we can see that our initial pressure might be overestimated, might be too high. So this was the pressure trend before starting production. You need to be cautious here because at that stage, at that point in time, below the gauge, you might have some drilling completion fluids, or if you like, the fluid weight below the gauge might be a bit different. So what you might have is an estimate of initial pressure, but it might not be the exact value of initial pressure. But we're going to use this one as a starting point. So if we go on our model, let's decrease this to 7100 roughly, so that's a bit too low. So you got about 7113. Here we go. So now my model matched this trend here. This is a simple exercise. Huh? If we look again at the PBU data, now it's the opposite. We match the PBUs early on, but as time increases, we can see that the match degrades. Okay, we underestimate the pressure. Looks like in our model we lack some energy. We need to provide a bit more energy. We need to bring this line here up to the actual data. One way to do this could be perhaps to increase the permeability. Okay, so let's use, say, 4 millidarcy. Okay, that's a bit better. So maybe 3.5. That's a bit better, it's not too bad. But if we look at the conventional derivative now on the log-log plot, now our model doesn't match the data anymore. You can see that our permeability is too high, We don't match the stabilization at 10 hours. So we need to go back to our permeability of 2.5. There you go. Another thing we could do is maybe to increase the distance to the boundary. Maybe let's say 700 feet. Again, it's better. It's not perfect, but it's a bit better. But now, if you look at the conventional derivative, you can see again that our model doesn't match the data anymore. Our simulation is shift towards the right as we increase. That wasn't a great zoom. As we increase the distance to the boundary, now our simulation is shift towards later time or towards the right, and we don't match the data anymore. So that again is not the solution. So we add 550. So now we are missing something here. And what we are missing is deconvolution. Okay, we match the model only using this conventional derivative, only using this short shut-in duration. but we got information over 9,000 hours, and we don't use that. We don't use any information here. So we need to investigate deconvolution, and we need to try to recover a reliable deconvolved response. So let's click on this icon here. And now we've got this deconvolution window with the deconvolution method and the settings. So we've got 4 methods for the deconvolution. The first one, which is deconvolution all extracted period, all data at once. So that basically means that we are using a conditioning coefficient equal to 1. We're going to provide the algorithm, the pressure data for all these selected PBUs, and the deconvolution algorithm is going to give us only one deconvolution, one deconvolved response. So it's equivalent of using a conditioning coefficient equal to 1. So in general, we don't recommend to use this method. Except, for example, if the wellbore storage and the skin is the same for all the PBUs, which is very unlikely. The second method is to separate the deconvolutions with a common PI. So basically, it's equivalent to have a conditioning coefficient equal to 0. We're going to feed to the deconvolution algorithm PBU data from this PBU, and it's going to extract a deconvolved response from this. So for each PBU, we're going to get different deconvolved response. So we feed to the deconvolution algorithm data from only one PBU, and it's going to extract deconvolved response from only this PBU, let's say. And then we can compare the different deconvolved response, and at late time, we need to make sure that they are consistent if they represent the boundaries. If they are not consistent, we can tweak the initial pressure. We've got the third method, which is to get the deconvolution on one reference period and the end of the other periods. So basically, this is using a conditioning coefficient between 0 and 1. Okay, conditioning coefficient of 1 for the first method, conditioning coefficient of 0, and conditioning coefficient between 0 and 1. So you can select your reference period with this one. So basically what we are saying here, we are using the final PBU, which is this one, as the reference period. So we're going to feed data into the deconvolution algorithm, data from this entire PBU, and data from late portion of previous PBUs. Okay, this is called kappa, but this is a method that existed before being implemented into kappa. Actually, this method, I think, was found for the first time by Michael Levitin around 2004 and was published by kappa around 2010. Instead of having conditioning coefficient in kappa, what we have is this line here, the delta T split. And we can move this line to grab a larger portion of previous PBUs. We're going to see this in practice. Then we've got the fourth method, which is a mix between these two here.